Hello and welcome to Algebra 2, Chapter 3.4, and today we're discussing linear programming. And this is really just an application of graphing systems of inequalities and what you can do with it. So our first word for today is optimization, and optimization means finding the maximum or minimum value of some quantity, right? So if you are a business owner and you want maybe to optimize production, I want the maximum objects produced, or maybe you want to minimize cost, and so that's where optimization comes in. And so linear programming is just one type of optimization tool. Linear programming is the process of optimizing a linear function, a linear objective function, subject to a system of linear inequalities called constraints. So we're going to have some linear inequalities, those are our constraints. We're going to graph our constraints, okay, and that is called the feasible region. And then we're going to find, what we're going to find is our vertices and try them in our objective function. So if the objective function has a maximum or minimum value, it must occur in this feasible region. Sometimes the feasible region is bound, sometimes it's unbound. There's some pictures on page 163, but what that means really is it's bound if maybe there's lines on all the sides, so maybe here's my overlapping region. That would be bound. So its maximum and minimum both occur in that area. But an unbound region maybe looks something like that, and then here's my overlapping. Well, my minimum probably occurs someplace in here, right? My minimum probably is down here someplace, but there is no maximum, okay? And so that system just wouldn't have a maximum value. So how do we do this? Well, in the first example here, I've listed out all of your steps. So the directions are to find the minimum and maximum values of c equals negative x plus 3y, okay? This is our objective function, okay? And to do that, we're going to start by graphing the constraints. And there's problems it's going to give you the constraints, and there's problems we're going to have to write the constraints. So it has given us these 4 constraints. So we're going to start by graphing them. X equals 2, remember you can change those inequalities to equal signs to graph them. X equals 2 is this line here, the line where all the x's are 2. And greater than 2 I would shade to the right, okay? And I'm looking for this overlapping region. X equals 5 is this right here, this line, the line where all the x's are 5. And I want less than that, so that's coming back this way. So at the moment I'm between the two. You can shade much better with pencil, just shade really lightly. Y equals 0. Well, y equals 0 is this line. And I want to be greater than it, so everything above that line. So hopefully you see now we're in, if I got rid of some of this. Let's see. Well, maybe I don't know how to get rid of some of this. Okay. Well, we might be stuck with it. All right, we are between the two uprights. We're in here. There we are. Okay. And we got one more to graph, and this one is going to start at 12. Let's see. Go black. Start at 12, and we're going to go down 2 over 1. So where this is going to differ from just graphing regular inequalities is that we really want to make sure we know where these cross. Those are your vertices, and we got to be really careful that we know our vertices. All right. And they all happen to be solid. You find these are solid more often. And if we plug in 0, 0, we're going to get zeros less than 12, which is true. So we're shading below this line. And my overlapping region is this kind of trapezoidal area right in here. That is my overlapping region. So number one, graph the constraints. Number two is find the vertices. Okay, so what are my vertices? Well, this one down here looks to be 5, 0. We have one right here that looks to be 5, 2. This one over here is 2, 8. And down here we have 2, 0. Okay, and so you can have any 3 on for number of vertices. 3 would be a triangle, 3 on up. Okay, so this one happens to have 4 vertices, got the vertices. Plug each vertex into the objective function, because every vertex is an x and a y, right? So C equals, we're going to start with 2, 8. Negative 2 plus 3 times 8, 24, 22. It's going to go down to 2, 0. Negative 2 plus 3 times 0 is negative 2. On over, trying to do them in order here. Negative 5 plus 3 times 0. So I'm plugging each one into my objective function. Negative 5 plus 3 times 2, there's positive 1. Hopefully you got the same thing there. Let me know if I messed up. It happens. Okay, so there we go. And so then it wants the maximum and the minimum values. So my maximum is actually negative 5. And my minimum is negative 5. My maximum is 22. And we could say that occurred at 5, 0, and 2, 8. But we just want those values there. Okay, so now that we've done one, next one will go faster. Okay, find the minimum and maximum of my objective function. So the first thing is graph the constraints. So x equals 0 is this line here, and x is greater than 0, we're going to the right. The next line starts at 2, goes up 2 over 1. We're down 2 back 1. And if we plug in 0, 0, we get 0 is less than 2, which is true. So we shade below it. Okay. And then the last one, let's minus x and get y equals negative x plus 5. And so we're going to start at 5 and go down 1 over 1, making sure that we know where we are intersecting. Okay. And this one, if we plug in 0, 0, we're going to get 5 is greater than 0, which is true. So we're going to shade on this side. And it looks like our overlapping region is everything in here. Okay, so identify the vertices. It looks like we just have 2. That one right there is 0, 2. And this one up here would be 1, 4. And by the way, if you couldn't find your vertices, right, you could do a system of equations and solve for them. And we're going to test both of them in our objective function. So C equals 0 plus 5 times 2. So there's 10. And C equals 1 plus 5 times 4. There would be 21. Now, maximum value, we're going to go with 21. Question is this 10 a minimum value, or could we get something less than 10? Would less than 10 ever occur? Like what happens if I plug in negative 10, 0? Would that be less than 10? Right? What if I plug in negative 100, 0? This one has no minimum because it's not bound on the bottom. This is going to keep going down forever. There is no minimum value. So we're just going to say no minimum value. All right, we're going to do one more. Okay, let's see if we can get through it even quicker. Graph the constraints. So x equals 0 is this line. And we want to make sure you're shading as you go. Greater would be on this side. You don't want to wait till the end to try to figure out where they overlapped. Next one starts at 2, up 1 over 1. Okay, and it's shading, if we plugged in 0, 0, 0 is greater than 2. 0 is not greater than 2, so we're shading on this side. And our last one starts at 6 and goes down 1 over 1. Here we go. And if I plug in 0, 0, you're going to get 0 is less than 6. That's true. So we're going to shade down here. And what you get is, I believe, all of them overlapped here in this nice little triangle. So what are your vertices? They are 0, 6, 0, 2, and 2, 4. Okay, so graph the constraints, locate the vertices, plug all the vertices into the objective function. So for 0, 6, I get negative 6. For 0, 2, I get negative 2. And for 2, 4, I get 0. So that's our maximum. And negative 6 is our minimum. All right, that's what we're going to do today. We'll finish up when you get to class. Let me know if you have any questions, and have a great day.